Most days, the sun feels permanent. It rises, sets, and nothing seems to challenge it. But imagine waking up one day knowing that, at some point in the future, the sun will stop working the way it does now. No sudden explosion, just slow changes that quietly erase oceans, atmospheres, and eventually the planets themselves. That future begins with processes already happening inside the sun today. Tonight, we'll follow those processes step by step, from deep inside the sun to the fate that patiently waits at the end of its life. The reason the sun feels so stable is not because it is eternal, but because its changes happen on a scale far slower than human experience. You might think of stability as something absolute, something that either exists or doesn't. But in astrophysics, stability is usually a temporary balance, a state where opposing forces cancel each other out just well enough to last for a very long time. The sun is stable in exactly this way, not because nothing is happening inside it, but because too many things are happening at once, all pulling in opposite directions, none of them winning outright. At the most basic level, the sun exists because gravity never stops pulling inward. Every particle inside the sun is constantly being drawn toward the center, squeezed tighter and tighter by the weight of everything above it. If gravity were the only force at work, the sun would collapse inward, growing denser and hotter until something drastic happened. But gravity is not alone. Deep inside the sun, another process pushes back, and it does so with remarkable consistency. Energy is being created at the center, not occasionally, not in bursts, but continuously, second after second, year after year. For billions of years, you might imagine that this energy is produced because the sun is already hot, as if heat itself were the cause. In reality, the heat is the result, not the reason. What truly matters is pressure. As gravity compresses the sun's core, it forces particles so close together that entirely new interactions become possible. Hydrogen nuclei, which normally repel each other, begin to collide under conditions that simply don't exist anywhere near the surface. From these collisions, energy emerges, and that energy creates an outward pressure that resists gravity's inward pull. This balance, inward collapse versus outward pressure, is what keeps the sun the size it is today. It's not frozen in place. It's more like a person leaning forward while pushing against a wall, constantly exerting effort just to stay where they are. The moment either side of that effort changes, the balance shifts. If gravity becomes stronger, the core compresses further. If energy production increases, the outer layers respond. The sun's calm appearance is the surface expression of an ongoing negotiation deep inside. What makes this balance feel permanent to us is the pace at which it changes. The sun does not operate on human time. It doesn't react in years or centuries. Even its fastest internal adjustments take thousands of years to fully propagate from the core to the surface, and its slowest changes unfold over millions or billions of years. From our perspective, that slowness translates into reliability. Generations are born, live, and disappear while the sun seems unchanged. And so we naturally assume that what we observe now is what has always been, and what will always be. But if you step back and look at the broader picture, the sun is already well into a story that began long before Earth existed. It did not appear fully formed. It emerged from a cloud of gas and dust, shaped by gravity, influenced by earlier stars that had already lived through their own cycles. Those previous stars scattered heavier elements into space, enriching the material that would eventually become our solar system. The Sun inherited that material, not as something special, but as part of a continuous recycling process happening throughout the galaxy. You might think of the Sun as a unique anchor, something fixed at the center of our lives. But in the context of the Milky Way, it is one star among hundreds of billions, following patterns that astronomers see repeated again and again. Stars form, settle into long periods of relative calm, and eventually move on to new phases as their internal conditions change. The Sun's current state is not the beginning of its story, and it is not the end. It is the longest, most stable chapter, but it is still only a chapter. What makes this particularly easy to forget is how forgiving this chapter has been for life on Earth. The Sun's energy output has remained within a narrow range for an extraordinarily long time, allowing oceans to persist, climates to stabilize, and complex ecosystems to develop. Small fluctuations do occur, subtle changes in brightness and activity that scientists can measure, but none of them have pushed the system far enough to break that overall stability. From the perspective of biology and civilization, this has felt like a guarantee, yet that guarantee is not written into the universe. It is an outcome of specific conditions being met, conditions that depend on what is happening inside the Sun at every moment. Hydrogen continues to be transformed at the core, and as long as that transformation proceeds at the right rate, the balance holds. But nothing about that process is infinite. It is slow, extremely slow, but it is not static. With every passing second, the composition of the Sun changes just a little, and those tiny changes accumulate. You don't notice them in the same way you don't notice a clock's hour hand moving. But given enough time, the position is undeniably different. The Sun today is not identical to the Sun that shone over early Earth, and it will not be identical to the Sun that exists millions of years from now. The differences are subtle, but they are real, and they are moving in one direction. Understanding this doesn't require jumping ahead to dramatic outcomes or distant futures. It starts with recognizing that stability itself is something that has to be maintained, not assumed. The Sun is stable because it is actively balancing competing forces, not because it has reached a final state. And once you see it that way, once you stop thinking of the Sun as a static object and start thinking of it as an ongoing process, the rest of the story begins to unfold naturally, not as a surprise, but as a continuation of what is already happening. If the Sun is stable today, it is only because gravity once pushed it into motion. Long before there was light, long before there was anything we could recognize as a star, there was only a cold, diffuse cloud of gas drifting quietly through the galaxy. You might imagine this cloud as empty space with a few atoms scattered here and there. But in reality, it was vast, massive, and heavy with potential, made mostly of hydrogen and helium, mixed with traces of heavier elements left behind by earlier generations of stars. Nothing about that cloud suggested urgency. It could drift like this for millions of years without doing much at all. What changed was not the cloud itself, but its surroundings. Somewhere nearby, a massive star reached the end of its own long journey and released a powerful disturbance into space. That disturbance did not arrive as fire or light in any dramatic sense. It arrived as pressure, a slow-moving compression that rippled through the cloud and nudged parts of it just far enough out of balance for gravity to finally take over. Once gravity gained a foothold, even a small one, it began to amplify itself. Regions that were slightly denser than their surroundings pulled in more material, and as they grew heavier, Their pull became stronger. Gas that had once drifted aimlessly now began to fall inward, accelerating as it did so. As these regions collapsed, they didn't fall straight down into a single point. They spun. Any tiny amount of rotation present in the original cloud was magnified as the material shrank, flattening into a rotating disk with a growing concentration at its center. At the heart of this collapsing structure, pressure began to rise. As gas piled onto gas, particles were squeezed closer together. And with that compression came heat, not because something ignited, but because motion itself was being converted into thermal energy. You might think of heat as something added from the outside, but here it was generated naturally, simply because gravity refused to let the material stay spread out. At this stage, the forming sun was not yet a star in the way we usually imagine one. It didn't shine visibly. It was wrapped in dust, glowing faintly in wavelengths we can't see with our eyes. Astronomers call this phase a protostar, but the name can be misleading. It wasn't a miniature sun waiting to turn on. It was a system in flux, still growing, still falling inward, still collecting mass from its surroundings. Material from the rotating disk continued to spiral down toward the center, feeding the protostar and increasing its pressure and temperature. At the same time, some of that infalling material was redirected outward along the forming star's rotation axis, launched away in narrow streams that carved channels through the surrounding cloud. These outflows were not signs of instability or failure. They were part of the process, a way for the system to shed excess angular momentum while continuing to grow. As the central region grew hotter, it crossed thresholds that mattered. At first, those thresholds changed nothing fundamental. Gas became ionized. Particles moved faster. Pressure increased. But then, at a temperature of several million degrees, something subtle but decisive happened. The core became dense and hot enough that hydrogen nuclei began to interact in a way they never could before. You might imagine this as an ignition moment, like striking a match. But that analogy doesn't quite fit. There was no sudden flash, no single instant where the sun switched on. Instead, the process crept into existence. A few rare interactions here, a few more there. But once they began, they changed the rules of the system. Energy was no longer coming only from gravitational collapse. It was now being created directly at the center. This is the moment the sun entered its long main phase. Not because it had reached a final form, but because it had found a new way to resist gravity. The energy produced in the core generated pressure that pushed outward, countering the inward pull that had built the star in the first place. Collapse slowed, then stopped. The sun settled into a size determined not by chance, but by balance. You might expect that once this balance was achieved, the sun would simply remain as it was. But balance in astrophysics is never static. It is maintained through constant adjustment. If gravity compresses the core slightly more, energy production increases. If energy output rises, the core expands just enough to reduce the reaction rate. These feedback loops act like a natural regulator, smoothing out extremes and keeping the system within a narrow operating range. This is why stars like the sun can appear calm for billions of years. Not because nothing is happening, but because too much is happening for any one process to dominate. The sun is not a frozen object suspended in space. It is an engine running continuously, correcting itself at every moment. As the sun stabilized, its intense radiation and energetic outflows began to clear away the remaining gas and dust from its immediate surroundings. What was left behind was a flattened disk of material orbiting the young star, gradually clumping together into larger bodies. Over time, those clumps became planets, moons, asteroids, and comets. The solar system did not form alongside the Sun as a separate event. It emerged as a consequence of the same gravitational collapse that created the star itself. From our vantage point, billions of years later, it's easy to see the Sun as the fixed center and the planets as secondary additions. But in reality, they are part of the same story. The Sun's mass, its rotation, and its energy output shaped the environment in which everything else took form. Even now, the structure of the solar system reflects conditions that existed during those early stages. What matters for the larger story is not just that the Sun formed, but how it formed. It was built by gravity, stabilized by energy production, and locked into a long-lived state that allows complexity to arise around it. This state is remarkably durable, but it is not permanent. The very mechanism that prevents collapse also sets the clock for what comes next. Every moment, the Sun remains stable. Hydrogen continues to be transformed at its center. The supply is enormous, vast beyond human intuition. But it is not endless. The Sun's ability to hold itself up depends on this process continuing at the right rate. And while that rate changes only slowly, it does change. You might be tempted to think that these details belong to the distant past, that they matter only for understanding how the Sun came to be, not where it is going. But the opposite is true. The way the Sun formed determines the way it evolves. Gravity built the furnace, but the furnace itself will eventually reshape the structure that gravity created. To see how that happens, we need to look closer, not at the Sun as a whole, but at the precise place where mass becomes energy, where the balance that defines the Sun is continuously renegotiated. Deep inside the core, deep inside the Sun, far below anything we could ever observe directly, there is a region where the rules that govern everyday matter quietly give way to something more subtle. You might imagine the core as a violent place, chaotic and explosive, but in reality, it is defined by patience. Conditions there are extreme, yet remarkably steady, maintained not by sudden reactions, but by processes that succeed only because they fail so often. The core is small compared to the rest of the Sun, occupying only about a quarter of its radius. But nearly all of the Sun's energy originates there. Pressure is immense, created by the weight of the entire star pressing inward. Temperatures rise into the tens of millions of degrees, not because the Sun is burning in a conventional sense, but because particles are packed so tightly that motion itself becomes intense. In this environment, hydrogen nuclei move at tremendous speeds, constantly colliding, constantly repelling one another. You might think that with so much energy and so many collisions, fusion would be easy. In fact, classical physics suggests the opposite. Hydrogen nuclei carry positive electric charge, and like charges repel, under normal conditions, they simply bounce off each other, no matter how fast they move, even in the Sun's core. Calculations show that the odds of two protons overcoming this repulsion directly are essentially zero. If classical rules were the whole story, the Sun should never have begun shining at all. And yet, it does. Not because the barrier disappears, but because nature allows a workaround. On very small scales, particles do not behave like solid points with exact positions. They behave like waves, spread out, blurred, uncertain. This uncertainty allows for a phenomenon known as quantum tunneling, where a particle can pass through a barrier it does not have the energy to climb over. It is not common. It is not efficient. It is simply possible. In the sun's core, this possibility is enough. Out of an almost unimaginable number of collisions, a tiny fraction succeed. 2 protons come close enough. Their wave-like nature overlaps just long enough, and one of them changes identity. A proton becomes a neutron, forming a new nucleus. Energy is released, not in a dramatic burst, but as a subtle redistribution of mass itself. You might expect that once fusion begins, it cascades rapidly. But that intuition doesn't hold here. Fusion in the sun is slow by design. An individual proton can wander the core for billions of years before ever participating in a successful reaction. What keeps the sun shining is not the likelihood of fusion, but the sheer number of particles involved. With so many protons packed into such a small volume, even rare events become reliable when averaged over time. This slowness is not a flaw. It is the reason the sun has remained stable for so long. If fusion were easy, the sun would burn through its fuel quickly and violently. Instead, it releases energy at a controlled pace. Governed by probabilities rather than flames, the sun shines not because it is efficient, but because inefficiency stretches its lifetime. Each successful fusion reaction converts a tiny amount of mass into energy, exactly as Einstein's equation predicts. The mass difference is minuscule, but multiplied by countless reactions every second. It becomes the steady output that powers the entire solar system. High-energy photons are created in the process. Carrying this energy outward, nearly massless particles are released as well, slipping through the surrounding material almost without interaction, escaping the sun long before light ever does. Those escaping particles provide quiet confirmation that these reactions are truly happening where theory says they should, long before we could observe the sun's interior in any direct way. Detectors on Earth began registering signals that could only come from the core itself. They arrived seconds after being created, passing through planets, rock, and bodies as if none of it were there. A faint but constant reminder that the sun's engine never stops. What matters for the larger story is not the exact sequence of reactions, but the role they play. Fusion does not simply produce energy. It regulates the sun's structure. When the core compresses slightly, temperatures rise. Fusion becomes marginally more likely, and energy output increases. That extra energy pushes back, easing the compression. When the core expands, reactions slow, pressure drops, and gravity regains the upper hand. This feedback keeps the system hovering within a narrow range of conditions. You might think of this as a thermostat, but it is not tuned by intention or design. It emerges naturally from the physics of particles under pressure. The sun does not know how to maintain balance. It simply follows rules that make balance the most likely outcome, at least for a while. Yet even here, in the most stable region of the star, change is quietly accumulating. Every fusion reaction alters the composition of the core. Hydrogen is slowly replaced by helium, a heavier element that behaves differently under pressure. This transformation happens so gradually that it leaves no immediate mark on the sun's surface. From the outside, everything appears the same. Inside, however, the conditions are evolving. Step by step. You don't see this evolution any more than you see a calendar page turn while you're staring at it. But over long spans of time, the difference becomes undeniable. The core today is not the core it was when the sun first settled into balance. And it will not remain this way forever. The very process that holds the sun up is rewriting its interior. To understand how the energy created in this deep, dense region influences the rest of the star, and why changes in the core take so long to make themselves known, we need to follow that energy on its long, indirect journey outward, through layers where motion becomes confusion and time stretches in unexpected ways. Energy created in the sun's core does not behave the way intuition suggests. When we think about light, we tend to imagine something fast, something that moves freely once it exists, crossing space almost effortlessly. That image works well in empty space, but inside a star, it breaks down almost immediately. The moment energy is released in the core, it enters an environment so dense and crowded that direction loses its meaning. You might think that once light is produced, the hardest part is over, that it simply needs to travel outward and escape. In reality, creation is only the beginning. Inside the sun, light is not a messenger racing toward the surface. It is a prisoner surrounded on all sides. The region surrounding the core is packed with charged particles, mostly protons and electrons, arranged so tightly that photons cannot move more than a tiny distance without being intercepted. This vast interior layer is known as the radiative zone, and it occupies most of the sun's volume. It is not dramatic to look at, not turbulent or explosive, but it is one of the most consequential regions in the entire star. Here, energy moves not by bulk motion of material, but by a slow, repetitive process of absorption and re-emission. A photon travels a fraction of a millimeter, collides with a particle, disappears for a moment, then is re-emitted in a new direction, carrying slightly less energy than before. You might imagine this happening a few times, perhaps slowing the photon down. But the reality is far more extreme. This process repeats again and again, not thousands of times, but countless times over spans that dwarf human history. Each interaction erases any sense of where the photon came from or where it is going. Forward progress becomes a statistical accident rather than a goal. If you were able to trace the path of a single photon through this region, it would look nothing like a straight line. It would resemble a chaotic scribble, looping back on itself, wandering aimlessly, sometimes moving outward, sometimes inward, sometimes sideways. The photon still travels at the speed of light between interactions, but its net movement is so slow that speed itself becomes irrelevant. What matters instead is patience. The timescale involved is difficult to fully appreciate. Estimates suggest that energy created in the sun's core can spend hundreds of thousands of years trapped inside the radiative zone before reaching regions where escape becomes easier. During that time, the original photon ceases to exist in any meaningful sense. Its energy is redistributed, broken down into lower energy photons, transformed step by step until what eventually reaches the outer layers bears no resemblance to what was first produced. This long confinement acts as a powerful stabilizing force. It means that the sun cannot react quickly to changes happening deep inside. Any fluctuation in energy production is absorbed, diluted, and spread out over immense periods of time. Sudden variations are smoothed away, stretched until they become gentle trends rather than abrupt shifts. From the outside, the sun appears calm because its interior is filtered through this vast temporal buffer. You might think of the radiative zone as a kind of memory, holding onto energy and releasing it slowly, almost reluctantly. Without it, the sun would be far less predictable. Changes in the core would reach the surface much more rapidly, potentially leading to dramatic swings in brightness and structure. Instead, The star behaves with deep inertia, responding sluggishly, as if reluctant to reveal what is happening within. There is another subtle consequence of this delay. The light warming Earth today does not represent the Sun's current internal conditions in any immediate sense. It reflects processes that took place long ago, under circumstances that no longer exist in exactly the same form. In that way, sunlight is not a real-time broadcast. It is an echo, shaped by layers that slow, soften, and regularize what emerges. This separation between cause and effect is easy to overlook because it has no noticeable impact on daily life. The sun rises, the day warms. Seasons follow their familiar rhythm. Yet beneath that familiarity lies a profound disconnect. The sun's surface is always slightly out of sync with its core, responding not to the present moment, but to a distant past. As energy continues its slow outward drift, conditions gradually change. Density decreases. Particles are spaced farther apart. Interactions become less frequent. The random walk does not end suddenly, but it begins to loosen. Motion starts to resemble progress again. Even if it remains indirect, the energy has been reshaped by its confinement, moderated by countless encounters, stripped of extremes. By the time it approaches the outer regions, the energy is gentler, more orderly, better suited to escaping the star's grip. What finally emerges near the surface is stable enough to support environments far beyond the sun itself. The long imprisonment has done its work, transforming something violent and intense into something predictable and sustaining. This slow release also explains why the sun can appear unchanged across entire civilizations. The star we see today is the product of processes unfolding on timescales far longer than memory or record. Its apparent consistency is not evidence of permanence, but of delay. The sun is not frozen in equilibrium. It is moving so slowly that motion becomes invisible. Inside the radiative zone, energy does not flow. It waits. It accumulates to diffuse and leaks outward with extraordinary restraint. This restraint is not imposed from the outside. It arises naturally from the density and structure of the star itself. The sun's calm exterior is earned, paid for in time, as energy finally reaches regions where material can move more freely, where heat is carried not by photons alone but by the motion of plasma itself. The character of the star begins to change. The quiet patience of the interior gives way to something far more dynamic, a layer where energy no longer wanders aimlessly, but rises and falls in vast, visible patterns. If you could somehow look at the sun up close, really close, the first thing that would surprise you is how alive it feels. Not alive in a poetic sense, but in a physical one. The surface does not sit still. It never has. It shifts, boils, rearranges itself constantly, as if the star were breathing. This happens because energy, after spending an almost absurd amount of time trapped deep inside, finally reaches a region where light is no longer the most efficient messenger. Here, the material itself begins to move. Heat no longer waits patiently to be passed along particle by particle. It demands motion. This outer region is called the convective zone, and it makes up roughly the outer 30% of the sun's radius. That may not sound like much, but in absolute terms it is enormous. More than 200,000 kilometers thick. In this layer, temperatures drop from several million degrees to just a few thousand, enough for electrons to cling loosely to nuclei. That small change makes the plasma less transparent, trapping heat again. but this time with a different outcome. So what happens when hot material cannot easily release its energy as light? It rises. Just like water heating at the bottom of a pot, solar plasma becomes buoyant when warmed from below. It pushes upward, carrying energy with it. As it rises, it cools, becomes denser, and sinks back down. The result is a vast system of circulating currents, operating continuously across the entire star. You might ask, how fast does this happen? Surprisingly fast. Energy that took hundreds of thousands of years to escape the interior can cross the convective zone in a matter of weeks. Compared to the radiative zone below, this layer feels almost impatient, eager to move, eager to release what it has been holding. If you imagine boiling water on a stove, you get the general idea. But the scale is completely different. Individual convection cells on the Sun, called granules, are typically about 1,000 kilometers across. Each one is roughly the size of Texas, and there are millions of them visible on the surface at any given moment. They form, evolve, and disappear within minutes, replaced by new ones almost immediately. Telescopes reveal this granulation as a constantly shifting pattern of bright centers and darker edges. The bright regions mark where hot plasma is rising toward the surface. The darker boundaries trace where cooler material sinks back down. Nothing about the pattern is permanent. It flickers and reshapes itself endlessly, like foam on a turbulent sea. This is where another common misconception falls apart. The Sun does not have a solid surface. There is no crust, no boundary you could stand on. What we call the surface, the photosphere, is simply the depth at which the plasma becomes transparent enough for light to escape. Below it, photons are still trapped. Above it, they are free. The photosphere itself is surprisingly thin, only a few hundred kilometers thick, compared to the Sun's diameter of nearly 1,4 million kilometers. It is almost nothing, yet everything we see, the Sun's brightness, its apparent edge, the features captured in images, all come from this narrow layer. What we perceive as the Sun is really just the place where light makes its final exit. Temperatures here average around 500 degrees Celsius, hot enough to vaporize any known material, yet cool enough for magnetic forces to start playing a visible role. In some regions, those magnetic fields become so strong that they interfere with the normal upward flow of hot plasma. When that happens, sunspots appear. These dark patches are not holes or voids. They are areas where intense magnetic fields suppress convection, preventing hot material from rising, with less heat reaching the surface. These regions cool by a few thousand degrees and appear darker by contrast. Some sunspots are small and short-lived. Others grow larger than Earth and persist for weeks. Here's the counterintuitive part. Even though sunspots are darker, periods when they are most numerous often correspond to a slightly brighter Sun overall. Why? Because the surrounding magnetic structures, known as faculae, enhance energy flow nearby, more than compensating for the darker spots themselves. The total brightness can increase by about 0.1%. Small but measurable. This boiling surface is not just visually interesting, it matters. The convective motion constantly drags magnetic field lines around, twisting, stretching, and tangling them. The plasma acts like a conductor in motion, shaping invisible structures that store energy in tension rather than heat. even though the deepest roots of solar magnetism lie below this layer. The convective zone plays a crucial role in amplifying and transporting magnetic complexity upward. From far away, the sun still looks calm. A smooth disk, a steady light. But that calmness is a trick of distance. Just beneath the glow lies a restless environment. One that never repeats itself. One that balances enormous forces in real time. The contrast is striking. Deep inside, energy moves slowly and forgets its origin. Near the surface, energy surges upward in vast, visible patterns, reshaping the star from moment to moment. Both behaviors belong to the same system. One provides stability, the other provides expression, and woven through this motion, stretched and wound tighter with every rising and sinking current, is an invisible framework that will eventually dominate how the sun behaves. Not gently, but abruptly, it is already there, already growing more complex. Even if its presence is not always obvious. If the sun were only a ball of hot gas, its story would be far simpler. Heat would rise, light would escape, and the surface would quietly release energy into space. But the sun is not just hot, it is electrically active, and wherever charged particles move, magnetic fields follow. You don't see those fields directly, at least not at first. They don't glow, they don't announce themselves, yet they shape almost everything that makes the sun unpredictable. The flares, the storms, the sudden outbursts that can reach across the solar system all trace their origins back to an invisible engine hidden beneath the surface. The foundation of that engine lies in the sun's rotation. Unlike a solid object, the sun does not rotate as a single rigid body. Near the equator, it completes a rotation in about 24 days. Closer to the poles, the same journey takes closer to 34 days. This difference might sound minor, but over time it creates enormous shear inside the star. Below the convective zone, deeper inside the sun, rotation behaves differently. There, the material turns more uniformly, closer to a solid sphere. Between these two regimes lies a thin but crucial boundary layer known as the tachocline. It sits roughly 70% of the way out from the sun's center, and despite being relatively narrow, it plays an outsized role in shaping everything above it. Why does such a thin layer matter so much? Because it is where motion changes character abruptly. Imagine two adjacent lanes of traffic moving at different speeds. At the boundary between them, stress builds. Over time, that stress doesn't disappear. It accumulates. Inside the sun, that accumulation takes the form of twisted magnetic fields. Plasma in the sun is electrically conductive. When it moves, it drags magnetic field lines along with it. Differential rotation stretches those lines, winding them tighter and tighter around the star. Convection then lifts and distorts them further, folding them into complex loops. This continuous process of stretching, twisting, and amplification is what scientists refer to as the solar dynamo. The idea that the sun generates its own magnetic field was not always obvious. In the early 20th century, astronomers noticed dark spots on the sun's surface, but did not immediately understand their cause. It wasn't until 1908 that George Ellery Hale discovered that sunspots were magnetic in nature, using the Zeeman effect to detect magnetic fields thousands of times stronger than Earth's. That discovery changed everything. Sunspots were no longer just blemishes. They became visible markers of deeper magnetic structures breaking through the surface. Typical sunspot fields measure around 2,000 0 to quattro. 0, 0, 0, Gauss. For comparison, Earth's magnetic field at the surface is about half a Gauss. The difference is not subtle, but these magnetic fields do not simply sit still. They store energy, and like a twisted rubber band, the more they are stretched and tangled, the more energy they hold. The sun's surface becomes a staging ground where magnetic tension builds quietly, sometimes for days or weeks, waiting for a chance to release. You might wonder why this energy does not simply leak away gradually. Why does it erupt instead? The answer lies in the way magnetic field lines behave. Under certain conditions, they can suddenly snap into a new configuration, a process known as magnetic reconnection. When that happens, stored energy is released rapidly, heating plasma and accelerating particles in a matter of minutes. Before those eruptions occur, magnetic fields often form large looping structures that arch above the sun's surface. These loops connect regions of opposite magnetic polarity, usually within sunspot groups. They trap hot plasma, making them visible in ultraviolet and X-ray images as glowing arcs suspended above the surface. To picture this, imagine stretching a bundle of elastic cords between 2 points, then twisting them repeatedly. At first, they resist. Then, at some point, they slip, releasing tension all at once. The sun does this on a scale that defies everyday intuition. The convective zone plays a constant role in feeding this process. Rising and sinking plasma drags magnetic fields upward from below, distorting them further as they approach the surface. This motion does not create magnetism from nothing. It reshapes and intensifies what already exists, concentrating it into structures that can influence the star's behavior dramatically. Even when the sun appears quiet, this engine never stops. Magnetic fields are always being generated, always being twisted, always interacting with motion. The difference between a calm sun and an active one is not whether this process is happening, but how much energy has accumulated and where it is stored. There is a temptation to think of magnetism as an accessory, something layered on top of the sun's basic structure. In reality, it is woven into the star's behavior at every level above the core. The boiling surface described earlier is not just moving heat upward. It is sculpting magnetic architecture in real time. This architecture is not symmetrical. It evolves. It drifts. Over time, magnetic regions migrate across the surface, interacting with one another, merging, cancelling, or strengthening. Some configurations remain relatively stable. Others become unstable quickly. Predicting which will erupt remains one of the great challenges of solar physics. Space-based observatories have transformed our understanding of this invisible engine. Missions like SOHO, SODO, and Hinode have allowed scientists to watch magnetic fields evolve continuously, capturing the slow buildup of tension as well as the sudden moments of release. These observations confirmed that the sun's magnetism is not random. It follows patterns, even if those patterns are complex. What emerges from all this is a picture of the sun as a system with memory. Magnetic fields preserve information about past motion. They remember how plasma flowed days or weeks earlier. They carry that history forward, shaping future events. Heat alone cannot do this. Magnetism can, and this is where the sun's personality begins to change. Heat gives the star stability. Magnetism gives it mood. It introduces the possibility of sudden change, of events that unfold far faster than the slow processes governing the interior. The sun becomes capable of surprise. From Earth, most of the time, we don't notice. The sun still looks like a steady light in the sky, but the conditions that allow sudden eruptions are always being prepared beneath that appearance. The magnetic engine does not wait for attention. It works continuously, whether we are watching or not. This engine also connects layers that would otherwise seem unrelated. Motion deep below influences fields near the surface. Surface activity reshapes the outer atmosphere. Energy stored invisibly can be released in ways that send material and radiation far beyond the sun itself. All of this traces back to a simple fact: the sun rotates. And it does not rotate evenly. From that uneven motion, complexity emerges. From complexity, tension. From tension, the potential for sudden change. And once magnetic energy begins to escape the sun's surface, it does not stop there. It reaches upward, into regions where temperature behaves in ways that defy intuition, where the sun's atmosphere becomes hotter the farther you go, and where some of the most enduring mysteries in solar physics still remain unresolved. If you step back and think about it, the sun should become calmer as you move away from its surface. That's how heat works in everyday life. Walk away from a fire, and the air cools. Step back from a hot stove, and the warmth fades. Distance usually means relief, but the sun does not follow that intuition. And this is where its behavior starts to feel almost unreasonable. Just above the visible surface lies the sun's atmosphere, a region that at first seems thin and insignificant compared to the massive star beneath it. Yet this atmosphere behaves in a way that has puzzled astronomers for more than a century. Instead of cooling as you move outward, temperatures begin to rise again, sharply and unexpectedly. The first layer above the photosphere is called the chromosphere. It is only a few thousand kilometers thick, almost invisible against the sun's brightness, except during rare moments like total solar eclipses, when it appears as a thin reddish rim around the darkened disk. Its name comes from the Greek word for color, a hint that something unusual is happening here. Near the bottom of the chromosphere, temperatures hover around 4,000 to say 000 degrees Celsius, similar to the photosphere below. But as you move upward, instead of cooling, the plasma grows hotter, reaching tens of thousands of degrees. Why would gas become hotter the farther it is from the main energy source? That question alone kept solar physicists busy for decades. The chromosphere is anything but calm. It is threaded with magnetic fields and filled with constant motion. Thin jets of plasma, known as spicules, erupt upward from the surface at speeds of 20 to 30 kilometers per second. Each one lasts only a few minutes. But at any given moment, millions of them are active across the sun. They rise several thousand kilometers before falling back, like blades of glowing grass flickering in and out of existence. If you tried to explain this region using only heat flowing upward, nothing would make sense. The energy arriving from below is not enough to account for the observed temperatures. Something else must be injecting energy into the atmosphere, and that something is closely tied to magnetism. Above the chromosphere lies an even stranger region, the corona. This is the sun's outer atmosphere, extending millions of kilometers into space, fading gradually into the solar wind. During a total eclipse, the corona appears as a pale, ghostly halo with long streamers shaped by magnetic field lines. It looks delicate, almost fragile. In reality, it is unimaginably hot. Temperatures in the corona reach 1 to 2 million degrees Celsius, and in some regions even higher. This is not a rounding error or a measurement mistake. The sun's atmosphere really is hundreds of times hotter than its visible surface. How could that be possible? This mystery became clear only in the 20th century, when spectroscopic observations revealed that the corona emits light at wavelengths corresponding to extremely high temperatures. At first, scientists even proposed the existence of a new element, coronium, to explain the strange spectral lines. Only later did they realize those lines came from ordinary elements stripped of many electrons, something that can happen only in very hot plasma. So, where does the energy come from? One leading idea involves waves. The convective motions beneath the surface constantly jostle magnetic field lines, sending waves of energy upward. Similar to shaking one end of a rope, these waves travel along magnetic structures into the atmosphere, where they dissipate and heat the plasma. Another idea focuses on countless tiny magnetic reconnection events, sometimes called nanoflares, each too small to notice individually, but together capable of maintaining extreme temperatures. You might picture this like repeatedly bending a paperclip. Each bend releases a tiny amount of heat. One bend does almost nothing. Millions of bends add up. The sun's atmosphere may be heated not by a single dramatic event, but by an almost continuous drizzle of small releases of magnetic energy. What makes this especially difficult to study is scale. The structures involved are often far smaller than what telescopes could resolve until recently. Only in the past few decades, with missions like TRACE, Hinode, and the Solar Dynamics Observatory, have scientists been able to observe fine-scale dynamics in the chromosphere and corona in real time. These observations revealed that the atmosphere is highly structured. Magnetic loops guide plasma into arches and funnels. Bright regions mark intense heating. Dark voids indicate open magnetic fields where material escapes into space. The atmosphere is not a smooth shell. It is a tangled, dynamic environment shaped almost entirely by magnetism. This is also where the sun begins to influence space far beyond itself. The corona is the source of the solar wind, a continuous stream of charged particles flowing outward at speeds of hundreds of kilometers per second. Near Earth, this wind carries roughly 1 million tons of material per second, shaping planetary magnetospheres and carving out a protective bubble around the solar system. Without the corona, there would be no solar wind. Without the solar wind, Earth's magnetic field would interact directly with interstellar space, and conditions on our planet would be radically different. What looks like a thin, ethereal atmosphere is in fact a powerful engine extending the sun's reach across billions of kilometers. There is a certain irony here. The sun's core, where energy is produced, is hidden and inaccessible. The surface reveals motion but not origins. And the atmosphere, farthest from the source, is where the physics becomes most extreme and least intuitive. The farther you go, the stranger it gets. This inverted temperature structure also means that small changes in magnetic behavior can have outsized effects. Energy stored quietly near the surface can be funneled upward and released in regions where particles are already moving at tremendous speeds. The atmosphere becomes primed for sudden activity. From a distance, the sun still appears serene, but its atmosphere tells a different story. It is restless, overheated, and constantly restructured by invisible forces. The calm disk we see from Earth is just the base of a much larger, more volatile system. Understanding this atmosphere is not just an academic exercise. It is the stage on which many of the sun's most disruptive events unfold. It is where energy, patiently accumulated and carefully structured, can finally escape in dramatic ways. And once that energy breaks free of the atmosphere, it does not simply fade into space. It travels outward, sometimes in focused bursts, sometimes in massive clouds, carrying the sun's influence directly into the solar system, occasionally reminding nearby planets that their star is not always gentle. Most of the time, the sun releases energy quietly. Light escapes. Particles drift outward. Magnetic fields rearrange themselves without much drama. If this were always the case, the sun would be easy to live with, predictable, almost boring. But occasionally, the balance between stored energy and release breaks down. And when it does, the sun reminds us that calm is not its only mode. The key to these moments lies in magnetism. Magnetic fields in the sun's atmosphere are not static lines etched into space. They are flexible, elastic structures carried by moving plasma. As convection and rotation twist them, they become stressed. Energy accumulates, not as heat, but as tension. Like a spring wound, tighter and tighter. You might ask, how much energy are we talking about? The answer is unsettling. A single major solar flare can release around 10 to the power of 25 joules of energy in minutes. That is roughly equivalent to billions of 1 megaton nuclear explosions detonating simultaneously. And yet, this energy comes not from fuel being consumed, but from magnetic fields snapping into simpler configurations. Solar flares are the most immediate expression of this release. They occur when magnetic reconnection suddenly rearranges field lines, converting stored magnetic energy into heat, radiation, and particle acceleration. In a matter of seconds, plasma can be heated to tens of millions of degrees. X-rays and extreme ultraviolet light flood outward, followed by showers of energetic particles from Earth. These flares appear as sudden flashes in specialized instruments. Invisible light, they are subtle, but their effects can be profound. High-energy radiation travels at the speed of light, reaching Earth in just over 8 minutes. The same time it takes sunlight to arrive. That means there is no warning, only observation after the fact. Closely related, but even more consequential, are coronal mass ejections, often shortened to CMEs. Unlike flares, which are primarily bursts of radiation, CMEs involve the physical expulsion of matter. Huge clouds of plasma, threaded with magnetic fields, are hurled into space at speeds ranging from a few hundred to over 2,000 kilometers per second. To visualize a CME, imagine a magnetic loop in the corona growing larger and larger as plasma fills it, until the structure becomes unstable. When it finally breaks free, it carries billions of tons of material with it. Some CMEs expand to sizes larger than the sun itself as they travel outward, though the material inside becomes increasingly diffuse. Not every flare produces a CME, and not every CME is aimed at Earth. But when one is, the consequences can extend far beyond the sun. 1 to 3 days after eruption, the cloud can reach Earth's orbit, slamming into our planet's magnetic field and compressing it dramatically. When that happens, the result is a geomagnetic storm. Charged particles spiral along Earth's magnetic field lines toward the poles, colliding with atoms in the upper atmosphere. The most visible outcome is the aurora, shimmering curtains of green, red, and purple light dancing across the sky. Beautiful, yes, but also a warning sign, because the same currents lighting up the sky can induce electrical currents in long conductors on the ground. Power lines, pipelines, communication cables. The sun, 150 million kilometers away, suddenly becomes relevant to infrastructure built on Earth. History provides sobering examples. In September 1859, a powerful solar storm, now known as the Carrington event, struck Earth. Telegraph systems across Europe and North America malfunctioned. Some operators received electric shocks. Telegraph paper caught fire. Auroras were seen as far south as the Caribbean. At the time, the technology was primitive. Today, the consequences would be far more severe. A more recent example occurred in March 1989. A CME triggered a geomagnetic storm that collapsed the power grid in Quebec within minutes, leaving 6 million people without electricity for 9 hours. Transformers overheated. Protective systems failed. The sun did not need to be at its most extreme. It only needed to be energetic enough. You might wonder how often events like this occur. Large flares and Earth-directed CMEs are relatively rare, but not exceptionally so. The Carrington event is estimated to be a once-in-a-century scale storm. Smaller, yet still, disruptive events happen far more frequently. In 2012, a CME of Carrington-like strength narrowly missed Earth, crossing our orbit just days after our planet passed through the same region of space. Had the timing been slightly different, modern society would have experienced a very different week. The vulnerability today is far greater than in the past. Satellites are particularly exposed. Energetic particles can damage electronics, degrade solar panels, and interfere with navigation systems. GPS signals can become unreliable. Radio communication, especially at high latitudes, can be disrupted or lost entirely. Even at lower intensities, solar activity has subtle effects. During geomagnetic storms, Earth's upper atmosphere heats and expands, increasing drag on satellites in low orbit. In February 2022, a modest storm caused dozens of newly launched satellites to lose altitude and burn up in the atmosphere because engineers had underestimated this expansion. Astronauts are also at risk. Outside the protection of Earth's atmosphere and magnetic field, radiation exposure during a strong solar event can reach dangerous levels. Future missions to the Moon and Mars must account for this, designing habitats and warning systems that can respond quickly. Despite all this, it's important to remember that these events are not random tantrums. They are the natural outcome of processes that have been building quietly over time. Magnetic energy does not appear suddenly. It accumulates, is stored, and eventually finds a way to release itself. What makes prediction difficult is complexity. The sun's magnetic field is not a single structure, but a constantly evolving web. Small changes in configuration can have large consequences. A region that appears stable can become unstable in hours. A minor rearrangement can trigger a cascade. Modern observatories monitor the sun continuously, watching active regions rotate into view, measuring magnetic field strength and complexity. Space weather forecasting has improved dramatically, but it remains an inexact science. We can often say when the sun is more likely to erupt. Saying exactly when, how strong, and in what direction remains a challenge. There is a temptation to think of these events as anomalies, interruptions in an otherwise gentle story, but they are part of the same system that produces light, heat, and stability. The sun's ability to support life over billions of years does not come from being quiet. It comes from being regulated. These outbursts remind us that stability does not mean inactivity. It means balance. And balance, when pushed far enough, responds. After each eruption, the sun does not collapse into chaos. Magnetic fields reorganize. Energy levels drop. The system resets, ready to begin accumulating tension once again. The cycle continues, sometimes calmly, sometimes violently, and over longer timescales. These events do not occur at a constant rate. They follow patterns, rhythms embedded in the sun's magnetic behavior itself. Periods of relative calm give way to periods of heightened activity, not by chance, but as part of a larger cycle that governs how often the sun is likely to surprise us. Those cycles introduce another layer to the story, one where silence can be just as meaningful as violence, and where long-term trends quietly shape the odds of disruption long before any flare ever ignites. If the sun only erupted at random, it would be terrifying in a very different way. Chaos is harder to live with than danger you can anticipate. But when astronomers began watching the sun carefully over long stretches of time, they noticed something unexpected. The outbursts were not evenly spaced. They clustered. Quiet periods gave way to busy ones. Then quiet returned again. The sun, it turned out, had a rhythm. The most visible sign of this rhythm is the changing number of sunspots. Some years, the sun's surface is dotted with dozens of dark regions at any given moment. Other years, it appears almost spotless, smooth and unmarked for weeks at a time. This pattern was first documented systematically in the mid-19th century by the German astronomer Samuel Heinrich Schwabe, who noticed that sunspot numbers rise and fall in a cycle lasting about 11 years. This 11-year pattern, now known as the Schwabe cycle, became the first clue that solar activity follows an internal clock. During solar maximum, sunspots are abundant. Magnetic complexity is high, and flares and coronal mass ejections become more frequent. During solar minimum, activity subsides. Sunspots nearly vanish, and the sun appears deceptively calm. You might be tempted to think of this like seasons on Earth, predictable and gentle, but the analogy only goes so far. The sun's cycle is not perfectly regular. Some cycles last 9 years, others stretch to 14. Some are weak, others are intense. The pattern exists, but it breathes. There is another layer to this rhythm that is less obvious but even more fundamental. Every 11 years, around the peak of solar activity, the sun's global magnetic field flips. What was once magnetic north becomes south, and vice versa, because it takes 2 such flips to return to the original orientation. The full magnetic cycle lasts about 22 years. This longer rhythm is known as the Hale cycle. This reversal is not a cosmetic change. It reflects a deep reorganization of the sun's magnetic engine. Field lines unwind, reconnect, and rebuild in opposite polarity. The process is slow, unfolding over months, but its effects ripple outward, shaping how active regions form in the next cycle. To visualize this, imagine twisting a rubber band back and forth. After enough twists in one direction, you reverse, unwinding what you built and winding it the other way. The sun does something similar, but on a scale measured in millions of kilometers and decades of time. One of the most striking pieces of evidence for this cycling behavior comes from a simple but elegant observation known as the butterfly diagram. When scientists plot the latitude of sunspots over time, they notice a pattern. At the beginning of a cycle, sunspots appear at mid-latitudes, around 30 degrees north and south of the equator. As the cycle progresses, new spots form closer and closer to the equator. By the time the cycle ends, activity clusters near the solar midline, seen all together, This migration resembles the wings of a butterfly, spreading and folding over time. It is not just visually striking. It reveals how deeply ordered the sun's magnetism really is, even when its surface behavior seems chaotic. But what happens when the rhythm itself falters? History provides a remarkable example. Between about 1645 and 1715, sunspots nearly vanished. For roughly 70 years, astronomers recorded little to no surface activity. This period is now called the Maunder Minimum, named after Edward and Annie Maunder, who later analyzed historical records and recognized its significance. During the Maunder Minimum, the sun did not stop shining. Days still followed nights. Seasons continued. But the magnetic engine appeared to be operating at a much lower intensity. The solar cycle did not disappear entirely, but its visible expression weakened dramatically. What makes this period especially intriguing is its coincidence with a cooler climate on Earth. Often referred to as the Little Ice Age, winters in Europe were harsher. Rivers like the Thames froze more frequently. Glaciers advanced in mountainous regions. Was the quiet sun responsible? The connection is still debated. Changes in solar output during the Maunder Minimum were small, on the order of a few tenths of a percent. Yet even small shifts, sustained over decades, can influence climate systems. The sun's variability may not control Earth's climate, but it can nudge it. This raises an uncomfortable question. If the sun can enter prolonged quiet phases, can it also enter prolonged active ones? Modern observations suggest it can. Some solar cycles are far more energetic than others. Cycle 19, peaking in the late 1950 seconds, was one of the strongest on record, producing exceptionally high sunspot counts and intense activity. By contrast, the current cycle has surprised scientists by ramping up faster than expected after a relatively quiet minimum. These variations matter because they influence the likelihood of disruptive events. A Carrington-scale storm is far more likely during a strong solar maximum than during a deep minimum. Quiet does not mean safe, but busy raises the odds. There is another subtle consequence of solar minima that often goes unnoticed. When solar activity is low, the sun's magnetic field weakens slightly, reducing its ability to deflect high-energy cosmic rays from outside the solar system. As a result, more cosmic radiation reaches the inner planets, including Earth. This means that during quiet solar periods, astronauts, high-altitude flights, and even satellites can experience increased radiation exposure. Not from the sun itself, but from distant supernovae and energetic events elsewhere in the galaxy. Silence, in this case, comes with its own kind of risk. You might think of the sun as a shield as much as a source. When its magnetic influence is strong, it protects the solar system. When it weakens, the galaxy presses in more closely. Activity and quiet are not opposites in terms of impact. They simply change the nature of the threat. What makes prediction difficult is that these cycles are not driven by a single knob that can be turned up or down. They emerge from the complex interaction of rotation, convection, and magnetism deep inside the star. Small differences early in a cycle can amplify over time, leading to very different outcomes a decade later. Despite decades of study, scientists still cannot reliably predict the strength of an upcoming solar cycle far in advance. Models improve, data accumulates, but the sun retains an element of autonomy, behaving according to rules that are understood in principle but difficult to calculate in detail. From a human perspective, these cycles stretch across generations. A single person might experience 5 or 6 solar maxima in a lifetime, rarely noticing their significance, yet over centuries, the pattern leaves marks in historical records, technological disruptions, and even subtle environmental changes. The important point is not that the sun is sometimes quiet and sometimes violent. It is that both states are part of the same long-term behavior. Calm is not a default. It is a phase. Violence is not an exception. It is a consequence. These cycles also remind us that stability is never absolute. It fluctuates. It drifts. It depends on probabilities rather than guarantees. The sun's rhythm buys us long periods of predictability, but it does not promise permanence. And as we zoom out further in time and space, another factor enters the story, one that has nothing to do with the sun's internal clock at all. Our star does not exist in isolation. It moves through a crowded galaxy, surrounded by other stars, all tugging subtly on one another as they orbit the Milky Way. Those external influences do not act on the scale of years or decades. They operate over millions and billions of years. And when they do, they can reshape the very architecture of the solar system itself, regardless of how well-behaved the sun happens to be. It's easy to think of the solar system as a closed arrangement, a neat clockwork of planets circling the sun in predictable paths. After all, those orbits have remained remarkably stable for billions of years. Earth has gone around the sun more than 4 billion times without missing a beat. So what could possibly disturb something that durable? The answer lies in a quiet assumption we rarely question. We imagine the solar system as an island, isolated, drifting through empty space. But the galaxy is not empty, and the sun is not stationary. It moves. Our star orbits the center of the Milky Way at roughly 220 kilometers per second, completing one galactic orbit every 230 million years or so. During that journey, it passes through regions of varying stellar density, sometimes drifting through relatively quiet neighborhoods, sometimes entering more crowded ones where stars are born, live, and die in closer proximity. From a human perspective, the distances between stars seem enormous. The nearest star system today, Alpha Centauri, lies more than 4 light-years away. That sounds safely distant, but on cosmic timescales, distance is not protection. Given enough time, close encounters become inevitable. You might ask, what counts as close in astronomy? Surprisingly, it doesn't take a direct collision to cause trouble. A passing star doesn't need to enter the inner solar system to matter. Even a flyby within a few hundred astronomical units can exert gravitational nudges that accumulate and propagate inward. To put that into context, Pluto orbits at about 40 astronomical units from the Sun. The outer reservoir of comets, the Oort cloud, extends tens of thousands of astronomical units outward. That vast halo is loosely bound and extremely sensitive to external disturbances. A star passing nearby can stir it like a spoon in still water. Astronomers have known for decades that stellar flybys can trigger comet showers, sending icy bodies inward toward the planets. Some of Earth's mass extinctions have even been tentatively linked to periods of increased comet impacts, possibly associated with such disturbances. But recent research suggests the influence may go much deeper. In the past few years, scientists have begun running large-scale simulations that include not just the gravitational interactions of planets, but also the statistical effects of passing stars over billions of years. One such study, published in 2025, modeled the next 5 billion years of solar system evolution while accounting for realistic stellar flyby rates based on data from the Gaia spacecraft. The results were sobering. When stellar encounters are ignored, the solar system appears extraordinarily stable. The odds of a planet being ejected or colliding with another remain very small. But when flybys are included, even distant ones, those odds increase noticeably. The reason is subtle. A passing star does not usually cause immediate chaos. Instead, it slightly alters the orbits of distant objects, especially in the outer solar system. Those small changes then propagate inward over time through gravitational interactions between planets. It's not a shove, it's a nudge, followed by another nudge, followed by millions of quiet adjustments. You might compare it to a long row of standing dominoes. A gentle tap at one end does not knock them all down instantly, but it can change their alignment just enough that later, unrelated movements have a greater effect. The system becomes more sensitive, more chaotic. According to these simulations, the probability of Pluto's orbit becoming unstable over the next 5 billion years rises to about 5% when stellar flybys are included. 5% might sound small, but in astronomical terms, it's significant. Pluto is not massive. It is not tightly bound. It lives in a region where the sun's grip is weakest. More concerning is what happens closer in. Mercury, already the most dynamically fragile planet due to its interactions with Jupiter, becomes even more vulnerable. The same study suggests that Mercury's chances of destabilization increase by roughly 80% when stellar flybys are accounted for. In absolute terms, that raises its risk of collision or ejection from under 1% to nearly 2%. 2% still sounds reassuringly low. But consider what that number represents. It means that out of many simulated futures, some end with Mercury colliding with Venus or plunging into the Sun. And when that happens, the disturbance doesn't stop with Mercury. The inner solar system can unravel in cascades. Earth fares better, but not perfectly. The probability of Earth being ejected from the solar system or suffering a catastrophic collision due to long-term gravitational instability rises to about 0.2% over 5 billion years when stellar flybys are included. Roughly 1 chance in 500. You might wonder whether that should worry anyone. After all, 5 billion years is a long time. Human civilization has existed for only a few thousand. But this story is not about fear. It's about understanding what stability really means. Stability is not the absence of disturbance. It is the ability to absorb disturbance without breaking. And even the most stable systems have limits. The likelihood of a particularly close stellar encounter is low, but not zero. Based on current models of stellar density and motion, there is about a 5% chance that another star will pass within 100 astronomical units of the Sun within the next 5 billion years. That's roughly twice the distance of Pluto's orbit. At that range, the effects would be dramatic. The Oort cloud would be severely disturbed. Comet orbits would be reshuffled. Some simulations show that such an encounter could destabilize multiple planets within a billion years of the flyby. Not 4 or 5. What makes this especially unsettling is that these events are largely unpredictable. Stars move relative to one another. Their paths are influenced by the gravitational field of the galaxy as a whole. While missions like Gaia have mapped stellar motions with unprecedented precision, predictions break down over very long timescales. The Sun itself has not always lived in its current neighborhood. Evidence suggests it formed in a much denser star cluster, where close encounters were far more common. Those early interactions may have shaped the outer solar system, influencing the orbits of distant objects and even determining which planets survived formation. In that sense, the solar system we inhabit is already the product of past encounters. It is not pristine. It has been nudged, sculpted, and rearranged before. What we see today is a configuration that happens to have lasted long enough for life to emerge. This perspective changes how we think about permanence. The planets do not orbit in perfect isolation. Their paths are not protected by some cosmic boundary. They exist within a galaxy full of moving masses, all exerting subtle influence. You might imagine the solar system as a calm lake. On the surface, everything appears still, but beneath that calm, distant disturbances send slow-moving ripples. Most fade before reaching the shore. Some do not. The sun's internal cycles, its magnetism, its outbursts, all operate on timescales we can observe or at least record historically. Stellar flybys operate on timescales that dwarf civilization. They remind us that even if the sun behaved perfectly for billions of years, external factors could still reshape the system. This does not mean chaos is inevitable. Most futures remain stable. Most simulations end with planets still in place. But the guarantee we often imagine does not exist. There is probability instead of certainty, likelihood instead of promise. The longer the timescale, the more probability matters. Over millions of years, unlikely events remain unlikely. Over billions, they begin to occur. Seen this way, the solar system is not fragile, but it is not immortal either. It survives not because it is untouchable, but because it has been lucky often enough, for long enough. And as we widen the lens even further, another realization emerges. The stability we've been discussing, planetary orbits, solar behavior, galactic environment, all of it is temporary in a deeper sense. Even if no star ever passed too close, even if every orbit remained pristine, the sun itself is changing in a way that no external influence can prevent. That change is slow. It is patient. It has been unfolding since the sun first settled into balance. And it will continue, regardless of what the galaxy does around it. When we talk about stability in space, we often mean something very specific without realizing it. We mean that nothing dramatic has happened recently, or that nothing dramatic is likely to happen within a human lifetime. That kind of stability feels solid because our reference frame is short. But physics does not think in generations. It thinks in probabilities stretched across deep time. The solar system is a good example of this difference in perspective. From the moment Earth formed, its orbit has remained remarkably consistent. Seasons have come and gone. The length of the year has barely changed. The sun has risen billions of times in the same place in the sky. It feels fixed, almost architectural. Yet, when astronomers model the solar system over hundreds of millions or billions of years, a different picture emerges. The system is not rigid. It is delicately balanced. Each planet pulls on every other planet. Not strongly, but persistently. Those gravitational tugs never stop. They accumulate. One way scientists study this is by running thousands of simulations with slightly different starting conditions. The differences might be as small as a millimeter change in a planet's position, or a fraction of a degree in its orbital angle. At first, all the simulations look nearly identical. The planets trace familiar paths. Nothing seems unusual. Then, slowly, the paths begin to diverge. This sensitivity to initial conditions is a hallmark of chaotic systems. Chaos does not mean disorder. It means that tiny differences can grow over time, eventually producing very different outcomes. Weather on Earth behaves this way. So do planetary orbits. Mercury is the clearest example. Its orbit is already slightly elongated and strongly influenced by Jupiter. Over long timescales, Mercury's eccentricity can increase. If it grows large enough, Mercury's orbit can cross that of Venus. Once that happens, the entire inner solar system becomes unstable. Statistically, this remains unlikely, even when stellar flybys are included. The chance of Mercury triggering a chain reaction that disrupts Earth's orbit remains small. But small is not zero, and over billions of years, 0 is the only number that guarantees safety. Earth's odds, estimated around 0.2% for severe orbital disruption over the next 5 billion years, might seem almost reassuring. 1 in 500 feels abstract. But imagine rolling a 500-sided die once every billion years. You don't need many rolls before rare outcomes begin to appear. This is what long-term instability really means. Not that disaster is imminent, but that permanence is not built into the equations. You might ask whether this kind of instability has happened elsewhere. The answer is almost certainly yes. Astronomers have observed exoplanet systems where planets follow wildly eccentric orbits, tilt steeply relative to their stars, or even orbit in opposite directions. Some systems show evidence of past ejections, where one or more planets were flung into interstellar space. Our solar system looks orderly by comparison, but that does not make it exempt. It makes it a snapshot of one outcome among many possible ones. There is another layer to this idea of temporary stability, and it has nothing to do with gravity between planets. It has to do with energy. The Sun is not a static object, even during its long, quiet main sequence phase. It is slowly changing. Every second, hydrogen in the core is converted into helium. That helium does not participate in fusion the same way hydrogen does. It accumulates as helium builds up. The core's composition changes. Its density increases. Its temperature rises to maintain balance against gravity. The Sun subtly adjusts over billions of years. These adjustments make the Sun brighter, not dramatically, but steadily. Astronomers estimate that the Sun's luminosity increases by about 10% every billion years. When Earth first formed, the Sun was significantly dimmer. Paradoxically, Earth was not frozen, thanks to atmospheric composition and feedback mechanisms. But that gradual brightening has consequences. In about 1 billion years, increased solar output is expected to push Earth's climate beyond a stable range. Even without any orbital disruption, oceans would evaporate faster than they can be replenished. Weathering processes would accelerate. The carbon cycle would break down. This is a different kind of instability. No collisions, no flybys, just slow, relentless change. You might notice a pattern emerging. Whether we look at orbital mechanics or stellar physics, the theme is the same. Stability exists, but it is conditional. It depends on timescale. It depends on context. It depends on what you are willing to ignore. For a civilization lasting thousands of years, Earth's orbit is effectively permanent. For a biosphere lasting billions, it is not. For a galaxy lasting tens of billions, even stars themselves are transient. This realization can feel unsettling, but it can also be grounding. It reminds us that the solar system was never designed to last forever. It was designed to last long enough for complexity to emerge, long enough for chemistry to organize itself into biology, long enough for intelligence to look up and ask questions about its own origins. From that perspective, stability is not an absolute requirement. It is a window that remains open for a time, then slowly closes. Importantly, none of the instabilities we have discussed so far require anything dramatic to go wrong. They are not failures. They are natural consequences of how physical systems evolve. Gravity does what gravity does. Nuclear fusion proceeds according to well-defined rules. No external mistake is needed. Even if the solar system were completely isolated, even if no star ever passed nearby again, even if every orbit remained pristine, the sun's internal evolution would still move forward. This is where all the threads begin to converge. The sun's cycles taught us that calm and activity are phases of the same process. Stellar flybys showed us that isolation is an illusion. Long-term simulations revealed that stability is probabilistic. Now, stellar evolution brings everything under a single constraint: time. Not time as we experience it, measured in days and years, but time as physics understands it, a parameter that cannot be paused, negotiated with, or avoided. The sun has been converting mass into energy since the moment it ignited. That conversion has a finite budget. When the hydrogen in the core is gone, the rules change. Not abruptly, not violently at first, but decisively. The balance that has held for billions of years will no longer be available in the same form. This is not a sudden ending. It is a transition, one that unfolds over tens and hundreds of millions of years. Slow enough that no single moment defines it. Fast enough, in cosmic terms, to reshape the entire inner solar system. If you step back and look at the full arc, from planetary stability to stellar aging, the message becomes clear. What we call normal is a phase, a very long phase, but still a phase. And like all phases in astrophysics, it exists because certain conditions are met. When those conditions drift, the phase ends. Not because something failed, but because something else becomes unavoidable. That inevitability is not a threat. It is a property of the universe. And understanding it requires letting go of the idea that systems are meant to persist unchanged. They are meant to evolve. The next stage of this story begins when the sun approaches the limits of its current balance. Not because of chaos, not because of external disturbance, but because its core chemistry quietly reaches a tipping point. That moment does not announce itself with a flare or an explosion. It begins deep inside the star, far from anything we could ever see directly. For most of its life, the sun exists in a delicate compromise. Gravity pulls inward, relentlessly trying to crush the star. Nuclear fusion pushes outward, releasing energy that resists that collapse. As long as these two forces remain balanced, the sun remains stable, predictable, and familiar. This state has lasted for about 4-6 billion years. But balance in physics is rarely permanent. It lasts only as long as the fuel that maintains it. Deep in the sun's core, hydrogen has been quietly disappearing. Every second, hundreds of millions of tons of hydrogen are fused into helium. The process is extraordinarily efficient, but it is not reversible. Once hydrogen becomes helium, it no longer contributes to the same fusion reactions that keep the core supported. At first, this change is subtle. The sun does not suddenly dim or flicker. Helium, being heavier than hydrogen, settles toward the center. Over billions of years, the core slowly becomes enriched with helium ash. The region where fusion can occur shrinks, You might imagine a campfire where the outer logs are still burning brightly, but the center has begun to fill with ash. The fire is still alive, but the structure is changing. Eventually, a critical threshold is reached. Hydrogen in the very center of the sun becomes scarce enough that core fusion can no longer continue. When that happens, something important breaks. The outward pressure that once countered gravity in the core weakens. Gravity immediately responds. The core begins to contract. This contraction is not an explosion. It is a slow inward collapse, driven purely by gravity. As the core shrinks, it heats up. This may sound counterintuitive, but it is a fundamental principle of stellar physics. Compressing a gas increases its temperature. As the core heats, a surprising thing happens just outside it. In a thin shell surrounding the inert helium core, hydrogen that was previously too cool to fuse suddenly reaches the right conditions. Hydrogen fusion reignites, not in the center, but in a shell. Shell fusion turns out to be more energetic than the original core fusion ever was. The energy released in this shell pushes outward, inflating the sun's outer layers. The surface expands dramatically. As it does, it cools. The sun's color shifts toward redder wavelengths. This is the beginning of the red giant phase. This transformation does not happen overnight. It unfolds over tens of millions of years. From an external point of view, the sun swells steadily, growing dozens, then hundreds of times larger than its original radius. At its peak, models suggest the sun's radius may approach 1 astronomical unit, roughly the current distance between the sun and Earth. That number deserves a pause. 1 astronomical unit is not an abstract scale. It is the distance that defines our orbit, our year, our seasons. A star expanding to that size would engulf Mercury without question. Venus would not survive either. Earth's fate becomes uncertain. Some calculations suggest Earth might narrowly avoid being physically swallowed by the sun's outer atmosphere, pushed outward slightly as the sun loses mass through stellar winds. Other models suggest atmospheric drag and tidal interactions would pull Earth inward, sealing its fate. But long before any physical contact becomes relevant, Earth is already lost. As the sun brightens during its red giant phase, its luminosity increases by hundreds to thousands of times its current output. Oceans would boil away. The atmosphere would be stripped. The surface would melt. Life as we understand it would have vanished hundreds of millions of years earlier. It is worth noting that this destruction does not require a dramatic event. There is no sudden blast, no stellar tantrum. The sun does not lose control. It simply follows the rules of stellar evolution. At this stage, the solar system becomes unrecognizable. The inner planets are either gone or transformed into scorched remnants. The asteroid belt is disturbed. Outer planets experience changes in temperature and radiation that dramatically alter their atmospheres. Even the sun itself behaves differently. Its rotation slows. Its outer layers become loosely bound. Strong stellar winds begin to carry mass away into space. Roughly 20 to 30% of the sun's mass will be lost during this phase. That mass loss weakens the sun's gravitational grip. Orbits of surviving planets expand outward. Moons drift. Rings spread. The architecture of the system loosens. You might wonder whether any of this could have been avoided. Could a star like the sun burn its fuel more efficiently? Could it evolve differently? The answer is no. The sun's mass places it in a specific evolutionary category. Stars much larger than the sun live fast and die violently, ending their lives in supernovae. Stars much smaller burn slowly for trillions of years, barely changing. The sun sits in the middle. Its fate is neither explosive nor eternal. This is not a failure state. It is a consequence of scale. What makes this phase especially striking is how quietly it begins. There is no single moment when the sun becomes a red giant. No alarm sounds. The process starts invisibly, deep in the core, with hydrogen quietly running out. From that point onward, the future is set. The sun can no longer return to its original state. The balance that defined most of its life cannot be restored. Yet even now, this is not the end. The red giant phase is dramatic, but it is transitional. The sun is not finished burning fuel. A new kind of fusion lies ahead, one that requires even higher temperatures and brings with it one of the most extreme events a star like ours will ever experience. That event happens when the contracting core reaches about 100 million degrees, when helium itself ignites. What follows is brief, intense, and deeply strange. A moment where the sun releases an enormous amount of energy in a way that never reaches its surface directly. It is the last major transformation the sun will undergo as a nuclear furnace. By the time the sun reaches the height of its red giant phase, almost everything familiar about it has already changed. Its size, its brightness, its influence on the surrounding planets. All of that is unrecognizable compared to the quiet star that once sustained life on Earth. Yet, even now, the sun is not finished transforming. Deep inside, the core continues to contract. The inert helium core, no longer supported by hydrogen fusion, grows denser and hotter as gravity compresses it further. Unlike the earlier stages of the sun's life, this core is now supported not by thermal pressure, but by quantum mechanics. Electrons are packed so tightly that a new form of pressure emerges. Electron degeneracy pressure, a consequence of the Pauli exclusion principle rather than temperature. This detail matters because it changes how the next stage unfolds. As the core temperature rises toward roughly 100 million degrees Celsius, conditions finally become extreme enough for helium nuclei to overcome their mutual repulsion and fuse. Helium begins converting into carbon and oxygen through what is known as the triple alpha process, in stars more massive than the sun. This transition happens gradually. The core expands slightly, cooling itself as fusion begins. But in a star of the sun's mass, the degenerate core cannot expand in response to rising temperature. So when helium fusion ignites, it does so explosively. This event is called the helium flash. The word flash can be misleading. From the outside, nothing dramatic is visible. The sun does not suddenly brighten. No burst of radiation escapes into space. But inside the core, an enormous amount of energy is released in a very short time, equivalent to the total energy output of the sun over millions of years. That energy does not destroy the star. Instead, it does something subtle but decisive. It breaks the degeneracy of the core, allowing it to expand and cool. Once that happens, helium fusion settles into a stable phase. For the next 100 million years or so, the sun enters a quieter chapter again. Helium burns steadily in the core, producing carbon and oxygen. Hydrogen fusion continues in a surrounding shell. The sun shrinks slightly from its most bloated red giant state and becomes somewhat hotter and bluer. In stellar terms, this is a brief calm after a long upheaval. But this calm is temporary. Helium, like hydrogen before it, is a finite resource. Once the core's helium is exhausted, the Sun faces a hard limit. It does not have enough mass to ignite carbon fusion. The temperatures required for that process remain out of reach. With no new source of energy available in the core, gravity resumes its work. The core contracts again, becoming denser, hotter, and increasingly compact. The outer layers respond by expanding once more, often more dramatically than before. The Sun enters a late asymptotic giant phase, becoming unstable, pulsating, and shedding mass at an accelerating rate. Strong stellar winds carry vast amounts of material away into space. Over this period, the Sun loses a significant fraction of its remaining mass. Its outer layers are no longer gently held. They drift outward, forming expanding shells of gas. Eventually, the core is exposed. What remains at the center is a hot, dense object roughly the size of Earth, composed primarily of carbon and oxygen. It is no longer capable of fusion. It shines only because it is still hot, radiating away the energy stored during its earlier life. Around this exposed core, the expelled outer layers glow. Ultraviolet radiation from the hot core excites the surrounding gas, causing it to fluoresce in vivid colors. From a distance, this structure appears as a planetary nebula, a glowing shell or series of shells expanding into the interstellar medium. Despite the name, planetary nebulae have nothing to do with planets. The term comes from early telescopic observations, where these objects appeared as small, disc-like shapes reminiscent of planets. In reality, they are among the most beautiful and fleeting structures stars like the Sun ever create. A planetary nebula lasts only tens of thousands of years, a blink of an eye in cosmic time. As it expands, it thins and fades, eventually merging with the surrounding gas of the galaxy. The elements forged inside the Sun, carbon, oxygen, and others, are returned to the cosmic environment. This material will not be wasted. It may one day become part of a new star, a new planetary system, perhaps even new life. The Sun's matter does not vanish. It changes form and location. At the center, the remaining core continues to cool. This final remnant is known as a white dwarf. A white dwarf contains about half the original mass of the Sun, compressed into a volume comparable to Earth. Its density is extreme. A teaspoon of its material would weigh tons. There are no fusion reactions inside it, no internal engine. It is a stellar ember, slowly radiating its residual heat into space. Over trillions of years, the white dwarf will cool further, fading from white to yellow, then to red, and eventually to black, becoming a black dwarf in theory. In practice, the universe is not yet old enough for any black dwarfs to exist. This is where the Sun's story as a star truly ends. No explosion, no collapse into a black hole, no dramatic final flare, just a gradual release of what remains, followed by a long, silent cooling. Seen from afar, the Sun's life is unremarkable in one sense. Millions, perhaps billions of stars in the Milky Way will follow a similar path. And yet, from another perspective, it is extraordinary, because around this ordinary star, for a brief window of time, chemistry crossed a threshold. Molecules organized, life emerged. Consciousness appeared and began asking questions about stars, time, and endings. The Sun does not know this. It does not need to. Its physics alone was enough. And when its light finally fades, the story does not end with darkness, but with redistribution. The same atoms that once powered fusion in the sun's core will drift through the galaxy, available for whatever structures come next. The last breath of a star is not a disappearance. It is a release. When you think about it carefully, the most extraordinary thing about the sun is not how it will end, but how unremarkable it feels while it lasts. Every morning looks the same. Light arrives through a window, touches the ground, warms the air, and life continues without hesitation. Nothing in that moment hints at nuclear reactions, quantum tunneling, or timescales measured in billions of years. And yet, all of that is happening anyway. The sunlight, reaching your eyes right now, began its journey deep inside the sun's core, where mass quietly became energy. That energy did not travel straight outward. It wandered, scattering, colliding, changing form, sometimes taking hundreds of thousands of years just to reach the surface. Only then did it cross space in a matter of minutes and arrive here, unnoticed, as part of an ordinary day. You could say that we are always living slightly in the past, illuminated by energy released long before human history even began. This perspective changes how endings feel. The sun's future is not a sudden loss, not a single moment where everything stops. It is a long sequence of transformations, each following naturally from the last. Hydrogen becomes helium. Helium becomes carbon and oxygen. Energy flows outward. Matter drifts away. What disappears in one place reappears somewhere else. Nothing is wasted. Nothing is abrupt. Even the idea that the sun is dying is, in some sense, a human framing. From the point of view of physics, it is simply changing states, moving through conditions that its mass and composition make unavoidable. The same rules that allowed the sun to shine also dictate how it will fade. There is something quietly grounding about that. We often imagine the universe as violent, unpredictable, full of catastrophes waiting to happen. And while extreme events do exist, the story of our star is not defined by sudden destruction. It is defined by patience, by balances that hold for astonishing lengths of time, then gently give way when their conditions are exhausted. You might notice how often human language struggles with this idea. We look for villains, failures, mistakes. We want causes that feel dramatic. But the sun's story offers none of that. There is no moment where it does something wrong. There is no deviation from its nature. Its entire life unfolds exactly as the equations predict. What makes this personal is not the physics itself, but our position within it. We exist during a narrow window when the sun is stable enough to support liquid water, chemistry complex enough to allow life, and time slow enough for evolution to explore countless possibilities. That window is not infinite. It never was. But it is wide enough that something remarkable happened inside it. Awareness. At some point, the matter produced in ancient stars assembled into brains capable of asking where light comes from, why it lasts as long as it does, and what happens when it no longer does. The sun does not care about those questions, but the fact that they can be asked at all is inseparable from the sun's long, steady behavior. Every element heavier than hydrogen in your body was forged under stellar conditions, either in stars like the sun or in much more massive ones that lived fast and ended differently. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it passed through environments far more extreme than anything Earth will ever experience. In that sense, you are not simply under the sun. You are part of a much older process that includes it. Sometimes it helps to imagine the solar system not as a stage built for life, but as a temporary arrangement that happens to allow it. The planets will move, the sun will change, the galaxy will rearrange itself. None of these processes care whether someone is watching. And yet, for now, someone is. The stability we enjoy is not fragile, but it is also not guaranteed forever. It exists because certain conditions are met at the same time. Gravity holds. Fusion continues. Orbits remain orderly enough. External disturbances remain small enough. That combination will not last indefinitely. No combination ever does. But impermanence does not diminish meaning. If anything, it sharpens it. Knowing that sunlight is borrowed rather than owned changes how you think about it. It becomes less like a background feature and more like a long-running gift. One that has been quietly arriving every day without asking for attention. You might never need to think about red giants, helium flashes, or white dwarfs again. Daily life does not require that knowledge. But understanding that the ordinary warmth on your skin is part of a much longer story can shift perspective in subtle ways. The sun is not a constant because constants do not exist at this scale. It is a process, unfolding at a pace that feels static only because human time is so short. The fact that we experience it as steady is not an illusion, but it is incomplete. There is a future where the sun looks nothing like it does now. There is a past where it looked different as well. We happen to live in the middle, where its behavior feels predictable enough to fade into the background. That is not something to take for granted. Long after Earth is gone, long after the sun has shed its outer layers and settled into a quiet remnant, the atoms that once made oceans and organisms will still exist somewhere, drifting through the galaxy, available for new structures, new stars, new stories. Physics does not end things, it rearranges them. For now, though, the sun still rises. Its light still reaches us. Its internal clock continues ticking through reactions that began billions of years ago and will continue for billions more in different forms. And inside that long, indifferent timeline, there is a brief moment where the light is just right. The conditions are just right. And someone can pause long enough to notice that none of this had to happen exactly this way. That moment is where we are living now. All of this leads to a simple realization. The sun is not a background object in our lives. It is a process we happen to be living inside of. For a short while, at a very specific moment in its history. Not at the beginning, not at the end, but inside a stretch of borrowed light that is steady enough to feel permanent and rare enough to be worth understanding.